Hi, this is the team L Square from Campus Santa Fe, and we're going to present to you our proposed solution for the Puzzlebot Jetson challenge. To complete this challenge, we needed to involve many different techniques and technologies, but we're going to present to you the three main components to make the Puzzlebot solve the challenge: navigation, vision, and deep learning. First, navigation. Here, what we did was a line detection model to then implement classic control logic and be able to follow the line throughout the whole course. We also implemented a point-to-point navigation that used odometry to navigate through intersections while considering traffic lights and signals. In navigation, we also had to implement all the final modules into one single controller, with which we could control every function as a whole and make the Puzzlebot solve the challenge.
In the segmentation part, we have the recognition of the black line at the intersection point with the purpose of implementing a controller that allows use to follow the black line. But in our implementation, we use predefined OpenCV functions such as find contours, image minimization, thresholds to limit the detection errors, CVT colors functions, bounding rectangles, and hawk circles, among others. An area of interest of the image is required to avoid noise from other areas of the camera in such a way to have flags that allow visualizing the behavior of the action with a true and false, to program a state machine that allows to see the value of the flags and moving from one state to another to carry out the good process of the path.
We employed deep learning in order to create responsive behavior in the Puzzlebot. The model was trained using a convolutional architecture with two convolutional blocks, a flattening layer, and fully connected layers. Our first proposal was a model which employed RGB images. Since this model exceeded 17 million training parameters, it could not fit into the Jetson development board. Then, we decided to preprocess the input images in order to normalize them and convert them to grayscale. This reduced the model's memory space to one-third of its original size. At first, the model was underfitting, mainly because the images from the dataset did not match our signal's data distribution. Then, we decided to implement data augmentation using image data generator object from the TensorFlow API and some images extracted from video frames obtained with the Raspberry camera. The resulting model surpassed 90% validation accuracy and could easily distinguish between different types of input signals.